Hello everyone, welcome to our talk. I'm Ji-won Park.
I am Dominic Winterer.
Today we will together present our approach for testing SMT solvers called Generative Type-Aware Mutation. This work is a collaboration with Chengyu Zhang and Zhendong Su. We first give a brief introduction to the SMT problem. Given a first-order logic formula phi, x greater than 0 and x less than 0, the SMT problem is to answer whether we could find an assignment for the variables in the formula that makes the formula become true. If we find such an assignment, the formula is satisfiable. For this formula phi, we cannot find any assignment for x that makes phi become true. Hence, phi is unsatisfiable. If we change the last 0 to 1, the new formula is satisfiable, since 0.5 is a satisfying assignment. SMT Solver is a tool for solving the SMT problem automatically. Given a formula phi, an SMT Solver will report the satisfiability of the formula. In practice, SMT formulas are usually represented by SMT-LIB language. For this example, the first line is the declaration of variable x. The second line is the assertion for describing the formula. The third line is calling solver to give the satisfiability of this formula. Many programming language related techniques depend on SMT solvers. For example, symbolic execution, solver-aided programming, program verification, static analysis, program synthesis, and so on. And some of the concrete examples you might have heard of are AWS's access management tool Zelkova and Ada Core's Spark. Let's see an example of a bug in SMT Solver. To check if a string is empty, we can either check the equality of the string to the empty string or check the length of the string is 0 as they are equivalent. So now, say we want to verify that string A is an empty string with an SMT Solver. Here on the left side, we get the correct result with the correct model. However, on the right side, we get a correct result, but with an invalid model. This is an actual bug we found with our Generative Type-Aware Mutation technique. We wanted to build a mutation strategy that could cover as much solving space as possible with a given formula. There are two very effective mutation strategies for stress testing software, which we generalize to build the Generative Type-Aware Mutation. First is type-aware operator mutation, which mutates the operators to their type-equivalent operator, and the second is fuzzing mutators, which mutates expressions. However, both techniques have limitations. Type-aware operator mutation is limited to operators only, and the size of the mutant is invariant. Fuzzing cannot generate new expressions with unseen operators. To overcome these limitations and generalize these techniques, we propose the Generative Type-Aware Mutation. Here, we will walk you through the Generative Type-Aware Mutations pipeline. First, we need a formula. From the formula, we randomly select an expression. For this example, we will use x. To mutate the formula, we will substitute x with another expression with same type as x, a string. To generate an expression, we first choose a random operator which returns string type. Also, the operator can only take arguments of types that are already presented in the formula. Here we have a string type x and integer type 0, hence we can choose an operator such as string from int or string concatenation. We choose string from int operator for now. Then we will additionally choose expressions with respect to the signature of the operator. As string from int takes an integer and returns string, we randomly choose 0 from the integer type expressions. Finally, we mutate the original formula by substituting the expression chosen at first by the generated expression. Then we use the mutant to test SMT solvers. Like type-aware operator mutation and fuzzing mutator, we're guaranteed to produce grammatically correct mutant. On top of that, as shown, the expression generated is bigger in size than the original, and contains an operator that wasn't previously available. This is an actual bug we found. CVC4 correctly returns set on the formula, but Z3 returns unset.
Thank you, Jiwon. I will now present the empirical evaluation. To evaluate generative type-aware operator mutation, we have engineered a tool called TypeFuzz. We built it on top of yinyang, the SMT Solver testing framework. With this tool, we conducted a bug hunting campaign from February 2021 until September. As the testing targets, we used the two SMT solvers Z3 and CVC4. We treated the solvers equally during fuzzing. As test seeds, we used formulas from the SMT-LIB benchmarks for strings, arithmetic and bit vector logics. Let's have a look at the results. The table shows our bug findings by status. Reported means we have filed a bug report on a public issue tracker. Confirmed means the developers have already confirmed that report as a bug. Fixed means the developers have already confirmed and fixed the bug. Duplicate means the developers have categorized our bug as duplicate and no further action taken. Totally, we have reported 237 bugs, 177 in Z3 and 60 in CVC4. Among these, 135 bugs were confirmed by Z3 developers, 54 were confirmed by CVC4 developers. Again, out of these, 132 are already fixed in Z3 and 44 are fixed in CVC4. Although we were very careful reporting bugs, we have also reported 14 duplicate bugs. This table shows the types among the confirmed bugs. We have found 73 soundness bugs, 49 in Z3 and 24 in CVC4. We have also found many crash bugs, in total 67. And we have found 49 invalid model bugs. This table shows the number of options among the confirmed bugs. Most bugs we found were in the default modes of the solvers, 55 in Z3 and 28 in CVC4. Notably, among these 28 were 18 soundness bugs in CVC4, which has proven to be a very stable solver. Among the 64 bugs with two options in Z3, 63 are in the new core of Z3. This is a configuration that Z3's main developer encouraged us to test. In fact, he said, "Thanks for targeting the new code. It is a very good use of the fuzzing facilities and helps reaching a more solid state of this so far not exercised code. All bugs reported in this thread have now been fixed." To understand whether generative type-aware and type-aware operator mutation are complementary, we have done a coverage comparison. For this, we have sampled 1,000 SMT formulas. We compared the seeds without mutation with OpFuzz, TypeFuzz and their sequential combination, and measured line coverage on both solvers. We made 3 observations. The first one is that both OpFuzz and TypeFuzz improve over the seeds. For OpFuzz, the increase is rather low. For TypeFuzz, the increase is higher. We also see that TypeFuzz covers more code than OpFuzz, since the second and third row dominate the first row. From the second to fourth row, we see that OpFuzz and TypeFuzz are slightly orthogonal, since the sequential combination of both tools dominate the second and third row. To understand the significance of TypeFuzz's bug findings, we investigated historic release versions. We have found 4 bugs that go back to Z3 4.5.0, which is 5 years old. In CVC4, we found 1 bug that goes back to version 1.5, which is 4 years old, latent. There were also 3 years latent bugs in the 1.6 release of CVC4. Now I want to show you some bug samples. Let me begin with Z3. This is a reputational soundness bug in Z3. Z3 incorrectly returns unset on this formula, while CVC4 gives set. The root cause of this bug was a missing sequence axiom. This is another soundness bug, this time in bit vector logic. The option configuration is Z3's new core and will be the future default mode. The old default mode correctly answers set, the new core returns unset, which is incorrect. It turned out that the root cause for this bug was a bug in Z3's floating point module. Here's another bug in Z3's new core. This time the formula is super simple, in linear arithmetic. The SMT solver is basically queried whether for all reals AB, the product of A and B is greater than B. Clearly this formula should be unset. However, Z3's new core reports it to be set. Now I'm going to show you 3 bugs in CVC4. Here we have a soundness bug on a string formula in CVC4. Z3 returns unset on the formula, while CVC4 returns set. The root cause of the bug was in the string rewriter of CVC4, which rewrites a replace expression to a prefix expression. The argument true in the check length 1 function ensures the second argument has exactly length 1. It could not be the empty string. The following bug shows a soundness issue in CVC5, which exists since version 1.5. Z3 returns set on this formula, which is the correct result. However, CVC4 1.5 and also 1.6 return unset on the formula. This bug was undetected for 4 years and has been found by TypeFuzz. This one is a crash bug on an arithmetic formula. When calling CVC4 on it, it throws a fatal failure. To sum up, SMT solvers are foundational tools for many PL technologies. To effectively test SMT solvers, we propose Generative Type-Aware Operator Mutation to overcome the existing limitation of operator mutation and pure expression mutation. We have engineered a practical tool called TypeFuzz. It has found many bugs in Z3 and CVC4. And among these bugs, many long-standing bugs in SMT solvers, undetected by previous fuzzing campaigns. For the future, we would like to extend TypeFuzz to more logics. We also want to experiment with integrating it into a continuous integration of SMT solvers. Finally, we want to generalize our technique to other applications beyond SMT solvers. TypeFuzz is integrated in the yinyang framework, which is on GitHub, and you can also install it via pip.